Okay, so we're going to continue the previous problem and then pick up with the rest of the review. All right, so we were looking at the force of friction. So we just ended with figuring out that the normal force was the same as the weight perpendicular. And so that gets us a frictional force of 14.3 newtons. So now, here's the catch. We know that it's going to slide because the weight parallel, so since the weight parallel is greater than the force of friction, we know it's going to slide. And in the next part, we're asked to figure out the acceleration of the block, so we know that A equals F net over M. But what we do not know at this point is what the net force is, because once I've established that it's going to slide, then we're no longer dealing with a static case, we're dealing with a kinetic case. So what I want to do, and just a little side calculation, so I want to redo the fun equation, but now I want to put in the 0.3. So if you put in 0.3 and multiply by the normal, we get a value of 10.2 newtons. So now I can do my sum of my forces, my 19.6 newtons minus my 10.2, all over 4 kilograms. And I got an acceleration of 2.35 meters per second squared. Okay, so now moving on to the free response questions, the IB free response questions. So I'm given this graph. Here we are. And so first of all, I noticed that it's a velocity versus time graph, and that there's a slight curve to it. Okay, and I say slight. So the first question is, what does this area represent? So what does that area represent? Now, you can do this in a variety of different ways. I like to think of it as areas. You're taking the bases and multiplying by the heights. Okay, in this case, we could approximate to be a triangle, but nevertheless, you have a meter per second multiplied by a second. So seconds divided by seconds cancel out, and we're left with a unit of meters, so we can get an idea that the area represents the displacement. So some of you may like to just memorize that. Some of you may like to do a unit analysis like I just did. Whatever works for you. So if I want to estimate it, notice it says estimate because I can approximate this to be a triangle where I have a base of 2 seconds and I have a height of 30 meters per second. And then the area of that triangle would be half the base times the height. So this is half of 30 times 2. So I get approximately 30 meters. And that's part B. Part C asks for the acceleration. So the acceleration on a velocity time graph comes in the form of the slope. But it's at 1 second. So what you have to do here is go up to where it hits 1 second. And I'm going to have a hard time doing this on the computer, but I have to draw in a tangent line. So use a straight edge, draw on a tangent line, that's not the best tangent line, and then find the slope of that tangent line. And then use the grid of the graph paper, find 2 spots that might cross the grid of the graph paper to find the slope. When I went through this, what I found was an acceleration of minus 12 meters per second squared. Okay, so try out this on your own and see what you got. And compare it. So if it's within 1 meter per second squared of that, that would be appropriate. So now if I want to figure out the magnitude of the air resistance, now if I just sketch the graph here, what I know is that the velocity starts off, the acceleration starts off big, and then sometime later the acceleration's less. So this is the VT. So I can look at the slope of the tangent line just to get an idea that the acceleration is decreasing, which means that the force is also decreasing. But I want to know what is that drag force at that 1 second worth of time, the 1 second worth of time. So I know that the object's being fired up, okay, so its velocity is up, and we also know that its acceleration is down. Drag is going against it, So if it's moving up, then drag's going down. So I know that the force diagram would look something like this, that I have some drag force, and then I have some force of gravity, some mg going down. So if I sum my forces and set that equal to ma, I have drag plus mg, plus because they're going in the same direction, equals my ma. If I subtract the mg over, I get ma minus mg, which if I pull out an m, this is a minus g, and that is equal to my drag force. And since I know a, I get my mass, which was 0.25 kilograms, so 0.25 kilograms times negative 12 minus negative 9.8. And so this is a positive there. And so if you go through and do that calculation, when I did it, I got a value of 0.55 newtons. Now, obviously, this is going to vary based on how your value will change. Your slope will change. So I got 0.55 newtons. All right, so the next one is asking, and this is actually what I was alluding to before, that I want to know what the force of air resistance is decreasing in magnitude as the ball moves upward, or with using the graph to explain it. And because I know that the slope is going down, that means that the acceleration is going down, and since mg is constant, if I look at the equation up above, I know that this value is constant. So if my a is going down, the only thing that could change on the left-hand side of the equation is the drag. So it's this series of logical arguments. The slope is going down. That means my acceleration is going down. Mg is constant. Therefore, drag must be going down. Okay? And you have to have all of that in there in order to get this correct. All right. The next one we're looking at, this is starting the multiple choice section. I'll probably do the first page here and then pick up the rest on the next video. So an elevator is used to raise or lower sacks of potatoes. In the diagram, a sack of potatoes mass 10 kilograms at rest, and then its accelerating the scale reads 4 kilograms. So what I know is that the scale reads a mass of 4, so it reads mg. Okay, so it's 4 kilograms times 9.8. I'm just going to write it as 4g. But normally, when it's not accelerating, it's 10 kilograms. So 10 kilograms times g. So what I can do is I can write the, first of all, notice that the force of gravity is greater than the normal force in this case. So I know that it's accelerating downward. So I can get rid of the two that say upward. And my acceleration is the sum of the forces divided by the mass. So I can write this as 10g minus 4g divided by the mass of 10. So this is 6/10 g, and that is approximately 6 meters per second squared downward. And notice, too, the best estimate. So call G10. This works. All right. So 2 blocks having different masses slide down a frictionless ramp. What I want to know is how does the force and the acceleration, how do they compare to each other? So what I do know is that when the block is sitting there, whatever block is on the ramp, that its accelerating force, its weight parallel, is equal to mg sine theta. So I do know that if there's more mass, there's more force. So I know that the forces are different. Okay, but now the question is the acceleration equal or different? So I know the acceleration is equal to the sum of the forces over m. like I said, the only force is the weight parallel. So this is mg sine theta divided by that mass. And so what we see is that the mass cancels out and the acceleration is just g sine theta. So the accelerations are independent of mass, so they're equal. Number 3 is we have a small boat in still water, is given an initial horizontal push to get it moving. Okay, notice that we're not going to keep on pushing it. The boat gradually slows down. Okay, so what I know is that there's no longer a forward force in order after the initial push. Okay, so anything that is talking about a forward force is incorrect. So now we know that there's some force going backwards, and the question, I mean, not that this is relevant here because there's only one choice that does not talk about a forward force. The diminishing with time, and that's because that as the drag goes across the water, there's a velocity dependence with drag, unlike friction. So therefore, that force, as it slows down, gets less and less and less and less. All right, and then the last one here on this page 5 is a ball is dropped and it's going to rebound off the pan. At the instant the ball has 0 velocity when in contact with the pan, the scale will read. Some of you may want to say that it's equal to W. But remind yourselves that even when the velocity is 0, the next instant of time, the velocity will be going up, meaning that the acceleration is up. So there's this upward acceleration, meaning that the upward force is got to be greater. So I'm going to call that the normal force because that's what it is. It's got to be greater than that weight of the ball in order for it to accelerate up. So the scale will read a greater value than W. So these two choices, conceptually, since we know it's accelerating up, we can eliminate. And then the reason C is not the case is the fact that it is, we know that it's not the first two choices because it has to be at least equal to W, but the reason why it's not W as well is because it has to accelerate up. All right, so we're going to stop this video at this point. I will pick up with the rest of the IB questions and all the Regents questions on the next video. Thanks for listening. Hope you've enjoyed it.